All right, so we have a couple equations that we have to introduce in this unit. Really, there's three units or three equations, one of which is actually in the waves section. So let me start with that one, and then we'll go through the rest of them after that. So the first equation that I want you guys to know about is the equation that describes the wavelength of a wave based on the velocity of the wave and the frequency of the wave. So this is the equation: wavelength equals v over f. This equation symbol right there is the Greek symbol lambda, which is wavelength. And in this class, we will be measuring it in meters, just like we've always measured distance type terms. Wavelength's not always measured in that. You'll see it in centimeters or nanometers if you do something in like chemistry or other branches of physics. But for classical physics, we're going to measure it in meters. Velocity is just going to be measured as you might expect. Uh, Velocity is going to be measured in meters per second. And when I'm talking about this velocity, I'm talking about wave speed. I'm talking about how fast the energy is moving. And then finally, we have frequency. And frequency is once again 1 over time, or 1 over period. So the official units are hertz, but a hertz is really just an inverse second. So don't be too confused by a hertz. It's really just a fancy way of writing 1 over seconds. So this is the first wave equation. And the big reason why this equation is important is because it teaches us some important stuff about the behavior of waves. One of the most important things to know and to take away from this is that wavelength is the variable that can change. This is the only one that changes based on the environment that you're in. Wavelength is allowed to change as waves are produced and do things. The other two variables are more fixed than that one is. So let's talk about how they're fixed and why. Velocity in particular, we'll start with. Velocity is determined by the material your wave is going through. So depending on what material you're sending a wave through, it will always go the exact same speed. An example of that right now would be the speed of sound. The speed of sound is approximately 340 meters per second. It doesn't matter what sound you make. High sounds, ha. Low sounds, low. That wasn't very low. I'm still a teenager. But whatever sounds that you're making, they travel at the exact same speed through the air. If we're talking about things like earthquakes, assuming that it's the same, the going through the same rock and some other things that make wavelengths or earthquakes a little bit weird, all earthquakes go the exact same speed. A big earthquake or a small earthquake still travels the exact same speed. So velocity is fixed by the material. You don't have to know those values off the top of your head. You just have to know that it is fixed. The other one that is fixed is the frequency. This is determined by the source. So when I talk, my voice, my vocal cords, whatever, is determining that I'm making high sounds and low kind of sounds. And once I've done that, it doesn't matter what material it goes through, my high sounds will stay high, my low sounds will stay low. If you put your head into a bucket of water and somebody's talking and they make high and low sounds, you'll still be able to tell that they're making high and low sounds. Their voice will get garbled because there's weird things that happen as it travels through the water, but the frequency is staying constant. That's also why you can hear through things like walls, hear through things like doors, because the frequency, once it's produced, travels through those walls, and then when it gets to the air again, it goes, it's still the exact same frequency, so you can hear what's being said. And you hear it more or less as it's being said, except with some loss in intensity because of the dispersion through the materials. So material and source both determine the velocity and frequency. That means that wavelength is going to be the thing that changes as I send a sound, for example, from me into the air, and then it moves into the water. The wavelength will change. The velocity will change at that air-water barrier. The frequency will be the same. Or if I right now I talk with a high voice or low voice, I am changing the frequency. The velocity will be the same through the air, and so wavelength has to change. So wavelength is the dependent variable in this equation. You should never talk about velocity or frequency changing unless you either know that the material changes or you're using some new source that could change the frequency. So that's the first wave equation. That's the one that's in the waves section on your formula sheet. The next one is also on the formula sheet, but it's kind of in a weird location. It's in the middle along the left-hand side, and it looks something like this. This is a wave equation that describes how a wave would look on a graph. It tells us the amplitude. We can use this part here to figure out what the period is, which means if we did 1 over t, we could figure out the frequency. It's basically the way that you would graph a snapshot of a wave. So A is amplitude and F is frequency. The rest of those things are variables that belong in the equation if you put them into the calculator. So I've very, very rarely ever seen this equation ever come up. I've actually only ever seen it show up in AP Physics 2. So it's unlikely that you'll ever be tested on this. If you are tested on this, though, I suggest that you just graph it. If you are on a computer and we're still in kind of like this distance learning mode, then open up Desmos, put whatever equations they give you into the graphing calculator on Desmos, and then pick the one that matches the answers. And if you have a graphing calculator, do it the same way. Basically, the only questions they ever have are something like, here's this graph, which one of these equations describes it? Or here's this equation, which one of these graphs describe it? And basically, in both cases, you just put the equation into Desmos or into a graphing calculator, and then you find the one that matches. That's all that really matters. They could, I guess, ask what the amplitude is. In that case, just look at what the height of the graph is. Or they might ask what the frequency is. And for that, you might just you'll either pull it straight out of the equation if they gave you the equation, or you could figure out period and go from there. But you're really pretty unlikely to see this equation. This last equation actually does come up, but it doesn't show up anywhere on the formula sheet. So this is the one that you want to record for yourself and maybe memorize, although it's not too hard to derive. So this is the equation for the average velocity of a particle on a wave. Not how fast the wave is moving, but how fast particles move up and down as the wave passes. And the equation for that you're going to use is 4 times the amplitude over the period. Or I guess you could do it 4 times the amplitude times the frequency. Either way would work. The whole point of this equation, or whole idea behind it, is if we know how long a period is, so that would be like from, I don't want to do it there. It would be like from this location to that location. We now know how long it takes for it to do an oscillation. So if it's that particle, we know how long it takes for it to go down, then back up. So that's a full wave. So we figured out the time that takes, and then we can say, okay, and during that time, it moves down, then all the way to the very bottom of the wave, then it moves back up, then it moves all the way back to where it started. So that's 1, 2, 3, 4 amplitudes. So really, this equation is pretty easy to figure out if you're given a graph, which is the way that this usually comes up. But otherwise, here's the equation for you. So these are the 3 big wave equations and some important information about how they work. Thank you for watching.